Hi everyone! Welcome to a vodcast that we are starting here in IC to help you get through your study guide for this unit. So here's the study guide posted here. It's on your class website. And also on your class website, this is underneath Unit 7, there is now a vodcast to help you get through the lab and also to get you started on the math required for the lab. It helps you to figure out what a millimole is and what the limiting reagents are and how to calculate the excess. So make sure you check that out if you need to, okay? But for now, we are going to be starting on our study guide. So grab an extra sheet of paper, a calculator, periodic table, and let's begin. Question number 1. If I burn methane gas and produce 5.59 milliliters of gaseous carbon dioxide at STP, how many centigrams of methane gas did I burn? And then it says how many milligrams of water were also produced. All right. In order to start a problem like this, the very first thing that you should do is to figure out what the balanced reaction is. So it says that methane gas is burning. Our first step is to get a balanced reaction. CH4 plus O2 will yield CO2 and H2O. That's a combustion reaction. Okay, does anybody confirm that for me? Can anybody confirm that for me? Thanks. All right, come back to the original problem. It says that if you burn methane gas and produce 5.59 milliliters of gaseous carbon dioxide, 5.59 milliliters of gaseous carbon dioxide at STP, how many centigrams of methane gas? How many centigrams of methane gas did I burn? And then the second question would be, how many milligrams of water were also produced? All right, let's start it off. You're starting with 5.59 milliliters of CO2. And this gas is at STP. So what we can do is convert that using your traditional conversion factor of 22.4 liters is equal to a mole. But you don't have liters. You have milliliters. You need to convert. How many milliliters are in a liter? Yeah, 1,000. There you go. And notice I'm cross-canceling. Okay. Now that I've got the liters up here, what can I put down here so I can get to moles? Because that's the heart of stoichiometry. What do I put down here? 22.4 liters. Nice. Is equal to a mole. And remember what you're on. You're on CO2. All right. So we're going to do in the first question, we're going to go from CO2 to methane. That's our first step. Let's go ahead and do that. So the mole-mole ratio between these two guys is 1 to 1. It's pretty easy. 1 mole of CO2 is going to need 1 mole of CH4 to burn. All right, you see how CO2 is there, CO2 is there. Always cross-cancel. All right, now the first question wants you to get to centigrams. Before we get to centigrams, you kind of need to get to grams first. So my very first step here is I'm going to convert the moles here into mass. Is that 16.0 grams, I'm pretty sure? Sweet. All right, you have one more step because I didn't ask you how many grams, I asked you how many centigrams, so I'm going to do one more step here. How many grams, or I'm sorry, how many centigrams are in a gram? Good job, that's how many cents are in a dollar. That's the way I remember it. All right, and see how everything is cross-canceling? All right, it is calculator time. How many sig figs do you think we should have at the end? Yeah, 3. She's working on a quiz. Careful. Okay, just don't talk to her. Oh, okay, didn't know that. 0.399 centigrams. How'd you guys do? Está bien? Great. So that was just one of the questions. The other question asked you, hey, how many milligrams of water were also produced? So we're going to make another problem for that. Start the same way. 5.59 milliliters CO2. We don't like milliliters, so we're going to convert that to liters. Same start here. Got to convert that to moles. And remember what you're working on. You're working on CO2. But this time we're going to go to water. Alright, so this time that mole-mole ratio is going to be a little different, okay? In front of CO2, there's no coefficient, but there is a coefficient in front of that water, so be careful. Always cross-cancel. Let's cross-cancel the CO2. You got 1 CO2. Sorry, I didn't get some room here. 1 mole of CO2 will also produce 2 moles of water. Alright, now on this water, I think they wanted milligrams, so we got to make sure that we convert to grams first, and then milligrams second. Alright, molar mass of water is 18. And now we just need to make sure we go to milligrams at the very end. Lots of milligrams in a gram. How many milligrams are in a gram, guys? 1,000. Alright. Let's do this one. 5.59 divided by 1,000 divided by 22.4 times 2 times 18 times 1,000. Alright, on this one I've got, and I'm going with 3 sig figs, 8.98, and that would be milligrams. Anybody confirm? Woo-woo! Alright, question number 1 is done. Alright, let's go to question number 2. Alright, if 4.6 grams of hydrogen peroxide decomposes into water and oxygen gas, how many molecules of oxygen can I produce? First things first, let's figure out what the balance reaction is. And by the way, this is one of your questions on the last test for types of reactions. So let's see if you guys did it right. So hydrogen peroxide, you're like, how do I get the formula of hydrogen peroxide? Well, peroxide is an ion. It is O2. It's actually a diatomic ion, and it has a -2 charge. So if you were asked what's the formula of hydrogen peroxide, you needed to know the charge of hydrogen. What's the charge of hydrogen? It is +1. So how do we make this balanced here? It is H2O2. Congratulations, you just got the formula of hydrogen peroxide without knowing what it was. Alright, now it told you that this is going to decompose into water and oxygen gas. Alright, let's balance it up. Got a couple right there. Let's see, and a couple of those right there. Alright, now that that's balanced, let's see what they want to know. Okay, let's go back to the question. 4.6 grams hydrogen peroxide. Hold on, let me get that down. 4.6 grams of this. What do they want to know? How many molecules of oxygen gas can I produce? They want to know how many molecules. Alright, you guys ready? Stoichiometry. Here we go. Start with what they got. 4.6 grams of the H2O2. Alright. So we're going to do a traditional stoichiometry problem, but we're going to end in molecules. Let's get that molar mass. 16 times 2 plus 2. I got a molar mass of 34.0 grams for this dude right here. Do you guys... Yeah, right. And that's 1 mole. H2O2. Alright. What comes next? Are you starting to predict? Mole-mole ratio? Alright, we're going from here to there. Coefficient on this guy is a 2. There is no coefficient here. So just make sure you follow your stuff, alright? You got hydrogen peroxide there, so I'm going to put hydrogen peroxide down here. 2 mole H2O2 will give you 1 mole of O2. Alrighty. Now remember, they want you to end in molecules, so how are you going to end at the very end of this thing? What are you going to put on the top here? Are you going to put it... Yeah, you can put that Avogadro's number. Alright, for 1 mole of oxygen, there will be 6.02 times 10 to the 23rd molecules. Alright, there we go. Math time. 4.6 divided by 34 divided by 2 times 6.02 to e 23rd. Alright, this is what my calculator says. 4.0723 blah 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 times 10 to the 22nd. How many sig figs do you think you need? It's a good talk. How many sig figs you got here? 2 is 4.6. How many here? 3. Do mole ratios count for sig figs? No. How many here? 3. So it's either 2 or 3. How many? 2. 1, 2. Do you need to round that last value right there? Do you need to round that up? Yes, because you got a 7 next to him. So this is 4.1 times 10 to the 22nd molecules. Final answer. Alright, question number 2 is done. Let's try question number 3. Alright, if I could react 5.3 times 10 to the 45th atoms of copper with plenty of oxygen, how many grams of copper 2 oxide could I produce? Alright, in order to do this, we kind of need to start with the balanced reaction. Always start with that balanced reaction. Alright, so we got copper. Copper's a metal. It is reacting with some oxygen gas. Make sure you know that that's diatomic. I think you guys are used to that now. And it told you that this is copper 2 oxide. That means your copper has a +2, and you guys know the charge of oxide is -2. And this is ionic. And guys, that is the black rusty stuff that's on a penny that's really old. That's what it looks like. That's what that is. So the outside of the penny is always oxidized. So, all right, is this balanced up? Not yet. Let's get it balanced. All right, now we're ready to roll. Let's see what they want to know. Go back to the problem. Let's see what they want to know. They are giving you 5.3 times 10 to the 45. Okay, so 5.3 times 10 to the 45 atoms of this. And they want to know how many grams of copper 2 oxide can you make? Question mark, grams. Alright, let's do it. Always start with what they provided you in the original problem. 5.3 times 10 to the 45 atoms of copper. Hey guys, how do we go from atoms of copper to moles? What do you gotta do? What do you guys need to do in order to go from atoms to moles? Avogadro's number. Where should I put Avogadro's number? On the top or on the bottom? Bottom. Good job. Alright, so that's how many atoms are in 1 mole of copper. Alright, cool. Now we're on moles. Yay, we can do this. Let's do that. It's a 2-to-2 ratio. For every 2 moles of copper, there will be 2 moles of CuO. See, I'm always cross-canceling. See how I'm following that? Alright, now they want us to end in grams, so I'm going to get that molar mass of copper oxide. Alright, let's see. Copper is going to be 63.5 and oxygen is 16. Alright, every mole of CuO has a molar mass of 79.5 grams. Ready? Here we go. 5.3 e to the 45 divided by 6.02 e to the 23 times 2 divided by 2 times 79.5. Alright, this is what my calculator says. 6.99916 times 10 to the 23 grams. Holy moly, that's a lot of grams. So what do you think? How many sig figs do you want? Do you want 3? Do you want 2? Look at that. That only has 2. Everything else has 3, and remember, mole ratios don't count. So you should only have 2, 1, 2. Oh my gosh, what happens to that 9? It will turn to a 0, which is in turn going to turn the 6 into a 7. Alright, 7.0 times 10 to the 23 grams. Hey guys, guess what? That's like the mass of the moon. That's nuts. That was like a pretend problem. Do you guys recognize that power? 10 to the 23? Avogadro's number? Yeah, that was like a crazy problem. I like doing those students. Yeah. Alright, here we go. If I react calcium acetate with potassium carbonate, what's going to be the precipitate? Alright, here we go. Okay, so you kind of probably want to get your solubility rules ready. Get some of your charges ready, okay, because we're going to be making an equation. We're going to make a formula. Alright, here we go. Calcium, Ca. I'm going to put his charge underneath just so that we can keep track. Acetate, that's a big fat ion, H2 or C2H3O2. He has -1 charge. So here is the correct formula for calcium acetate. They said that this guy reacts with potassium, that's a +1 charge. Carbonate, he's -2. So the correct formula for potassium carbonate is K2CO3. Alright, what kind of reaction you got? It doesn't even tell you what the products are, man. Yeah, it's a double replacement, so everything switches. Calcium is going to have a new buddy. That would be carbonate. This guy's +2, -2, so we're set. And the other guy is going to be potassium. He's +1. And the other ion that he likes is acetate, C2H3O2, and that's -1. Okay, solubility rules, peeps. You're going to want to grab that because there's a lot going on here. Alright, let's see. So we need to do solubility and we need to balance this thing. Tell you what, I'm going to balance it real quick because that's pretty easy. You guys see how there's 2 acetate ions? I'm going to come over here and get a 2. That gives me also 2 potassiums, which that's already got 2. Alright, let's see. Anything with acetate I know is aqueous. You guys can look at the solubility rules for acetate, but I know they're always soluble. Am I right? Pretty sure. Alright, anything with an alkali metal in the front is also soluble, right? So I know this is this guy right here. He is going to be aqueous. The only one that I am questioning is calcium carbonate. So you want to check that. What is the rule for carbonates? It's kind of picky here. I think it's one of those weird ones. Alright, I got my solubility rules. I'm checking that. Let's see, I'm going to read it out loud for you. All carbonates, etc., are insoluble except those of alkali metals and ammonium. Well, calcium is not an alkali metal, okay? He's an alkaline earth metal. Hey guys, I just found your precipitate. He's solid. Alright, so the answer here is calcium carbonate. This guy is your precipitate, okay? Right there. Okay. Question number 5. In the reaction above, so they're using the same reaction, if you have 15.2 grams of calcium acetate, hold on, 15.2 grams of this, and 19.2 grams of the potassium carbonate, hold on, 19.2 grams of this. Alright. What is my theoretical yield of the precipitate? So in other words, they want you to tell them how many grams of this can you make. Okay, so this is a limiting reagent problem. They started you with 2 quantities. That means we're going to have 2 setups. Alright, let's do it. So they want to know the theoretical yield. That means the maximum you can make of your precipitate. Alright, so here's one. And now we're going to set up the other one, starting with that 19.2 grams. Alright. There we go. So you're going to have 2 stoichiometry problems, and both of them need to go to the precipitate. Alright, here we go. This is going to take a bit of math, so I'd love it if you guys could help me check my molar masses, because I don't want to mess it up, especially not on a vodcast. Alright, I'm going to do this calcium acetate. Give me a second here. Alright, I got 158.1. Can anybody confirm that at all? Did anybody get that far? You didn't get that? No? Oh, you did though, Isabel? Anybody else confirm it for me, please? Check it one more time. I'll do it again too. calcium is 40.1. Let's see, carbon is 12 and you've got 4 of them. Hydrogen is 1 and you've got 6 of them. Oxygen is 16 and you've got 4 of them. I'm sorry, I got 158.1 again. I'm going with it. Alright, so that is 1 mole of your calcium acetate. Whoop. Alright, so in this problem, we are trying to go from calcium acetate to calcium carbonate. So the mole-to-mole ratio there is 1 to 1. For every 1 mole of the calcium acetate, there's 1 mole of your precipitate. Alright, let's get the molar mass of that guy. Calcium is 40.1, carbon is 12, oxygen is 16, and we got 3 of those. I got a molar mass of 100.1. Are we good? Alright, let's do some math. 15.2 divided by 158.1 times 100.1. Alright, for the first one, I got an answer of 9.62. I'm going to go with 3 sig figs. Alright, now we're going to set up the second one. That means technically you are going to have 2 different answers, right? Which one is going to be correct? The lesser amount is the maximum you can make. That will be your theoretical yield, okay? In case you can hear that over the vodcast, we have students working on Rube Goldberg machines, and they keep dropping their bowling ball. It's actually kind of cool that they're working on that. Okay, can you guys check my molar mass here? I got 138.2 for potassium carbonate. Now in this problem, we're going from here to there. Looks like there's a 1 to 1 mole ratio. For every 1 mole of potassium carbonate, you will make 1 mole of calcium carbonate. And what's really cool about doing these is once you get the molar mass of the precipitate for the first reaction, hey, you already did it. It's right there. 100.1 grams. All right, let's do it. 19.2 divided by 138.2 times 100.1. Okay, I'm going to give myself 3 sig figs. The answer here is 13.9 grams. Okay, everyone, which one is the maximum you can make? What's your theoretical yield? Yeah, the lesser amount. This is your theoretical yield. That is the maximum you can make, okay? I have another question. You ready? What is your limiting reactant? Which one ran out? Whatever made the lesser amount ran out. Your calcium acetate is completely gone. It's all gone. And I think I just answered a few problems there. Alright, so I got my theoretical yield. Let's see. I know which one's my limiting reagent. Which reactant will I have excess of, though? Which one is not completely consumed? Potassium carbonate. We have some of that left. We didn't use all of it. And the question is asking how much will be left. Whew. You ready? We know that we produced 9.62 grams of this precipitate. We know that the calcium acetate is completely gone. But the question is, if we made this much precipitate, how much of the calcium carbonate did we actually use? Because we didn't use all of it, but we did use some of it. So to answer that question, you need to set up a third problem, starting with the 9.62 grams of precipitate. So I'm going to start with the 9.62 grams of the precipitate, calcium carbonate. And I'm going to figure out, doing some stoichiometry, exactly how much of the potassium carbonate I use, because I didn't use all of it. So in this third problem, I hope you understand what we're doing is we're going from calcium carbonate to potassium carbonate to figure out how much we actually used. How much did it take to make that 9.62 grams? The best part about going backwards is you already have all of your molar masses done. All right, what's the mole ratio between these two guys? I think it's 1 to 1. For every 1 mole of precipitate, you will need 1 mole of the potassium carbonate. All right, 1 mole of K2CO3 has a molar mass of 138.2 grams. All right, remember, this answer represents how much you used, not how much is in excess. How much was used. 9.62 divided by 100.1 times 138.2. We used 13.3 grams. How much was available to us? 19.2 grams was available. This is how much we were given in the problem. To figure out your excess, all you have to do is just subtract how much was used. All right, so 19.2 minus 13.3. You've got 5.9 grams left over. There you go. That's your excess. All right. Now, the last problem on this one is asking if I actually made 3.2 grams of the precipitate, what's my percent yield, and what is my percent error? All right, so you made 3.2 grams. Well, our theoretical, the amount we were supposed to get, was 9.62. So, percent yield is really easy. Percent yield, all I'd have to do is take what I actually got, which they told you is 3.2 grams. So 3.20 grams is what I actually got. And I'm going to divide it by what I should have got, which is 9.62 grams. 9.62 grams. Times that by 100. Let's see what we get. Okay. I got, and I'm going to go with 3 sig figs here, I got 33.3% yield. That is yield, percent yield. Percent error, you may have to review on the formula, but percent error is basically the difference between what you were supposed to get and what you actually got, so you have to subtract, that's what the difference means, and it's usually absolute value. And then you're going to divide by what you were supposed to get, one more time, that theoretical, and times 100. Alright, so let's do that. 9.62 minus 3.2 divided by 9.62 and times 100. Now when you do this on the calculator, you want to make sure that the numerator is kind of like a quantity, so you may want to put these like in parentheses before you hit divide. Alright, and my answer is 66.7 because I'm going to do 3 sig figs percent. Here's something that you guys probably never knew. This is called percent error here. Did you know that your percent yield plus your percent error will always be 100%? Because your percent yield is like how much you got out of what you were supposed to get, and this is basically how far you were from what you were supposed to get. So it kind of makes sense that those two, when you add them together, it's going to give you 100%. All right, everyone, we're going to stop here for now, and I hope this was helpful. Maybe Friday, maybe I'll do another vodcast if I can during IC. All right, you guys, have a great afternoon. Bye-bye.